A little bit more formal introduction. Foreman is a professor of engineering physics and director of the Center for Energy and Combustion Research. Not anymore. Okay, I got that wrong. At the University of California, San Diego. I think we all know him from using his textbook combustion theory. That's the first. That's the first book I used, and he has a wide list of awards, many articles that you all know of. I just mentioned that in 1990 you received the Bernard Lewis Gold Medal, which is the highest honor of the Combustion Institute. And
maybe if I stand up, it'll stop.
Yeah, and one more. Foreman is a member of the United States National Academy of Engineering. So. I'll stop. Thank you.
Okay. I'm not sure exactly how to handle this lecture because there are experts and experts and experts here. So I think the main thing is that I should restrict myself to 50 minutes. Is that it?
Yeah, if you have a discussion after that, of course.
Okay.
All right. Jim will come to that, I think.
So the subject that I thought could be interesting to discuss is the G equation and limitations of it, I think probably essentially everybody knows what the G equation is, so I maybe can go through the first part of this stuff pretty quickly. Actually, if people want to raise questions or discussions, right? That's something we
sure.
do. Okay. So the first thing I'll do is show a diagram of regimes of turbulent combustion, and then talk about flamelets, and that's where the G equation applies. Then I want to say some things about instabilities. No known to lots of you. I'm not sure how much interest there will be in the rest of this stuff, so I may or may not spend, depending on interested people, on lean hydrogen combustion chemistry and a model for flame propagation in lean hydrogen mixtures and the lean flammability limit of hydrogen. So that's kind of the plan of the outline, or at least it's the order in which these slides are here. So here is a regime diagram for turbulent combustion with the mean flow velocity vertically and the size of the combustor horizontally in meters per second. And there are lines on here corresponding to constant values of different properties. The flow time is the size over the velocity. There's lines of constant Reynolds number based on integral scale of turbulence. Lines of constant Kolmogorov scale of turbulence, and so on. There's a Froude number. Being put equal to 10 is a buoyancy limit. Buoyancy is important at low Froude numbers, and so this shows that fires are buoyancy influenced, whereas afterburners are high speed. Gas turbines, not quite so high speed. Internal combustion engines there. These are not buoyancy influenced. This diagram, who knows who wrote it down? Who wrote it first? Do you know? You should know. Bob Bilger.
Ferrari could be.
No, Bilger. This is from Bilger. Bilger is this is a dimensional diagram that I got from Bob Bilger, and I like it. It's practical. It shows you where the different But that was dimensional, and its non-dimensional diagrams are better. And so, as some of you saw, you were here on Monday, I suggest Reynolds number based on integral scale of turbulence and root mean square fluctuation velocity as a horizontal axis, and a Domkohler number based on the ratio of a large eddy turnover time of the turbulence to the chemical heat release time, overall chemical heat release time, as a vertical coordinate in a regime diagram. And this is certainly more. This is now related to the turbulence properties, and so it's more directly related, I think, to the physics of what's going on in combustion. And so this is the diagram of turbulence Reynolds number here from 1 to 10 to the 8th, and Domkohler number from 10 to the minus 4 to 10 to the 8th. Pretty much covers everything. I'm wondering, is it going to cover supernova? I really never asked myself that, whether I go far enough to cover supernova.
You have the just in distributed reactions, you have down at low Reynolds number.
Well, they claim it's distributed reactions, but I'm not so sure.
I mean, well-stirred reactor.
Yeah, well-stirred reactor would be down there, but they must have very high Reynolds numbers.
Yeah.
And what kind of Domkohler number effective overall Domkohler number do they have? I know there's a paper where they say that they're in the distributed reaction regime, but I don't necessarily believe that. So anyway, these are the different regimes, and the shape, and here I don't think I need to say in words what these lines are, because it says over here what they are. Point is that the shaded regime is what's called flamelet regime. So basically at high Domkohler numbers, the chemistry is fast compared with the turbulence time. And so when the chemistry is fast, the chemistry occurs in sheets that are flamelets. Whereas when the chemistry is slow compared with the turbulence time, the turbulence would mix everything up very much, and then that mixing would lead to distributed reactions. Reactions distributed through the turbulent mixture. I like this diagram for a fundamental reason that I like it is everything that I've just said could apply irrespective of whether the mixture is non-premixed or premixed, whether it's a diffusion flame or a premixed flame. You still have in the diffusion flame in the flamelet regime, then the chemistry is fast, so whenever fuel and oxidizer find each other in turbulent flow, they react in sheets where they're separating fuel from oxidizer. Diffusion flames locally, the reactants fuse into these sheets where the reaction rate is fast. And in the premix case, the fresh mixture is too cold to react, so that the chemical time is like infinite nearly in the fresh mixture. But then when it starts to react, it reacts very quickly, so that within the flame itself, the chemical time is short, the Domkohler number is high, and so when it reacts very quickly, the mixture again reacts as a sheet, and these sheets then move around in the turbulent flow. The G equation will apply as 90% of you know, only to premixed, not the non-premixed cases. And these different regimes on the diagram, sub-regimes, refer to premixed combustion. This is the weak turbulence regime, where the turbulent Reynolds number is small, the fluctuation velocities are small, and so in this regime you mainly have like a fast laminar flame propagating through a weakly turbulent fluid, a weak turbulence or wrinkled flame, slightly wrinkled flame regime. As the turbulence Reynolds number increases, the sheets become more and more wrinkled, and they become wrinkled enough so that they may break apart, and a wrinkled front may, if this is fresh, this is burnt, may come like that, and then these are propagating into each other, and then eventually they may cut off on pockets of fresh gas, so you may have fresh here, but no pockets of burnt gas, because because the flame does not propagate, would have to propagate into the burnt gas. Would have to unburn the fluid if we're going to make pockets of burnt. So it can't do that. So I call this a multiple sheet regime, and the idea that the shape of the sheet has a fractal dimension applies in this regime at high enough turbulence Reynolds number. That's a theoretical claim. This diagram is entirely equivalent to the classical Borghi diagram that everybody else uses except for me. The Borghi diagram has, for example, is just this diagram skewed in some direction. KL, turbulent kinetic energy, referred to ratio. See, I say ratio of kinematic viscosity to chemical time because that ratio would apply whether it's premixed or non-premixed, that description. If it's premixed, this ratio is simply the laminar burning velocity squared. And so this is intensity. Direction of increasing KL is direction of increasing, or increasing the square root of KL is the direction of increasing the ratio of turbulence intensity to laminar burning velocity in the premixed case, and that's one of the coordinates of the Borghi diagram. So you would skew the picture to obtain the diagram that many of you are much more familiar with. This multiple sheet regime is more commonly called the corrugated flamelet regime. And that is because in most practical combustion devices, people don't see these multiple sheets. Reynolds numbers aren't big enough to see multiple sheets, but instead you see highly wrinkled sheets, and they're called corrugated sheets, and so this would be the corrugated sheet regime this is the dump, and relevant Domkohler number, you can argue, would be based on the Kolmogorov scale, rather, and for some purposes anyway, rather than the integral scale. And so this this regime ends at a Dom-Kohler number based on Kolmogorov scale of 1. That's when you start to get turbulence inside in the interior of the laminar flame. And now up here, the turbulence scales are large compared with a laminar flame thickness, so you're really just wrinkling a sheet up there. Whereas from here to here, you start now to get turbulence scales that are comparable with the laminar flame thickness. And you all know that if you take a laminar flame, a premixed laminar flame, and look at the structure of the premixed laminar flame and plot, say, for temperature as a function of distance through the temperature of the unburnt gas, temperature of the burnt gas. In this flame, the chemistry really is on the hot side of the flame. And so there's this thin reaction zone. And a thicker than where heat conduction is and diffusion occur, preheat zone. Okay, so there's a reaction zone and a preheat zone. And the preheat zone then is larger than the reaction zone by the reciprocal of the Zolovich number, which is a measure of the dependence of the reaction rate. And so when you cross this line and move down here, the smaller scales of the turbulence now are comparable with the size of the preheat zone, but not yet comparable with the size of the thin reaction zone. So that gives rise to the thin reaction zone regime now, where now the turbulence is inside the flame, but still the reaction zone is not affected by the turbulence. Now, when the eddies now start to be comparable in size with the reaction zone, then they can break the reaction zone, and so you can have broken flamelets then here, and that's how you would move into eventually a distributed reaction regime. And so all of these things you can see on a diagram like this. These are specific IC engine calculations that actually put on this diagram. John Abraham, I think, was still a student of Rocco when I was at Princeton, who did those calculations for these specific engines. This is a general area in which spark ignition engine, diesel engines, as well as estimates for offshore flares would be to this round area. This larger area we've estimated for supersonic combustion. Gas turbines, I've not indicated here. They tend to be somewhat more toward distributed reactions, but most of the applications, the point is to make that the applications for the most part seem to be in this shaded flamelet regime, which is why we're interested in looking at flamelets and spend a lot of time looking at flamelets, more so than distributed reactions. It seems to me that even though we have not seen seldom see multiple sheets in terrestrial engine applications, I would think that supernova would be an excellent place to find these multiple sheets. So I don't understand why who was the author? Was it Bell or something? Or
He wasn't
No.
claiming that that was necessarily a supernova regime. He was saying that's as close as he could get. It's a very useful benchmark for modeling, but he's not necessarily claiming that that's a
Oh, no, no,
supernova.
what's wrong is number is a supernova. I mean, it's not necessarily enormous, but the density is huge.
No, it can be 10 to the 13, 10 to the 18.
What? Lewis number?
Reynolds.
Reynolds
Reynolds
number.
number.
Lewis number is 10 to the 3 to
Yeah, yeah.
10 to the 7.
But still, regardless of Reynolds number, the issue of Dom-Cohen number as to whether you're in distributed reaction. Bell's, what we called it ILAS, was deep in the well-stirred reactor regime. That was based on computational accessibility.
Okay, so it was only accessible computationally in the well-stirred reactor regime, but that doesn't. But that doesn't have anything to do with reality. Then I guess that's
It
what
turns
you're
out to be a useful benchmark. I mean, in terms of the mechanism, the reaction mechanism it shows, it's useful benchmark for a model that might extrapolate to supernova regimes. I'm going to talk about this actually.
Oh, okay, good. Okay, fine. So you agree that the supernova may be multiple?
But it starts, it crosses the whole diagram. It starts as a laminar flame, and it starts probably at the very top, and then it will go down.
I don't think it'll go down. I think it'll go. I mean, the question comes: what is the chemical time in the supernova?
Well,
And it'll be extremely short in the high temperature nuclear reaction part of it. So.
empirically, it seems to have to go to a detonation at some point, which means at some point you have to have low Dom-Cohen number, presumably, even if they don't quite understand how you get there. Exactly. And it doesn't have to be throughout the flame. You could have patches of low Dom-Cohen. It may not be the one parameter that describes the whole flame breadth.
Well, yeah, we could talk about supernovas a lot, I guess, but you will talk about them more. Good. But I would suggest maybe they really are out there. I don't think. Maybe. Yeah.
Herman, can I ask you?
Yes.
In fact, I wonder about supersonic combustion.
Yes.
The situation is not so clear for me because, in fact, usually we have a very high temperature,
Yes.
about 1000, for example.
Yes.
So the chemical time can be not determined by the flame, but by autoignition process.
Yes.
So,
Well.
in some sense,
yes.
we have to add something, the new X,
Yes.
the temperature, because we have the competition of two chemical times. So,
That's right.
so
Exactly.
it's not exactly for
There's
supersonic
more than
combustion.
one chemical time, and that's a limitation of a diagram like this because you have to pick
So
the
we have
chemical
to
time
we
to
have to
draw the
draw
diagram.
once more X.
Yes. Well, yeah, the trouble is you need more, too many dimensions. You also need a Lewis number dimension, for example. So the question, so there's some, I think, ambiguity about the relevance of what chemical time do you take? What's the relevant time? The drawing here is based on, and these regimes are based on taking the time to be the transit time through a laminar flame. That's a time. And so that's one possible, that would be one definition. And so, I don't know what the transit time through the laminar nuclear reaction flame is, but anyway, I think it may be short enough that it would be a high Dom-Cohen number situation. But okay, but other times are relevant as well. And in supersonic combustion, autoignition processes may be important. I agree with you, and that's a different chemical time. But this estimate is based on regime estimate is based on the time being the transit time through a laminar flame in this hot, turbulent situation. By the way, when we're talking about supersonic combustion, it's usually a diffusion flame rather than a premix flame. It's typically non-premix, and so. But still, I can use this diagram to discuss it. But anyway, probably that's enough time spent on the diagram. In these flamelet regimes, when it's pre-mixed, you can, there is a reaction sheet, and so G of some function of x, say of x, y, z, t equals 0, that equals 0 would be the location of the reaction sheet. So I should have put equals 0 there. In a premixed situation, in a non-premixed situation, I suppose in these you still could define a reaction sheet, but it's more convenient to work with mixture fraction Z, which is 1 in the fuel stream, 0 in the oxidizer stream, and which obeys then this simple advection diffusion equation without a chemical source term, because it's a conserved scalar chemically. The chemistry doesn't just converts fuel to products, but at a given mixture fraction, I guess. And so for non-premixed situations, Z in partially premixed cases, it may be useful to use both G and Z. This is just for the non-premixed flame with mixture fraction. If you look at mixture fraction coordinate and it's burning, then this is the oxidizer side, and this is the fuel side. And so the point is that temperature, fuel concentration, this would be for methane, stoichiometric mixture fraction for methane air is about 0.054, which is why I drew it over there. And this would be for oxygen in the air, almost unique functions of Z. So by looking at mixture fraction, if you are high enough Domkohler number, then all of the properties you're interested in are a function only of mixture fraction. And so if you have statistics of mixture fraction, then in principle you also have the statistics of everything else. This picture shows oxygen leakage through a hydrocarbon flame. If you do activation energy, high activation energy asymptotics, then because the temperature gradient is steeper here, the chemistry would, the fuel would be burnt less in the oxidizer side than the oxygen would be on the fuel side, and so actually the fuel would leak rather than oxidizer based on one-step activation energy asymptotics. But if you put real chemistry in with a separate, recognizing that radicals burn fuel and oxidizer rather than fuel burning oxygen, you find that actually oxygen leaks rather than fuel for all hydrocarbons at the lower Domkohler numbers. And this is one of the things that, Bob Bilger pointed out, that, well, maybe activation energy asymptotics are not all that good. Well, in that aspect of the chemistry, they're not. It's not that good. But okay. But this is the G equation. The point is that now in the premix situation, this front is propagating at some velocity, and so if the front is going to propagate at a velocity s, the local flame propagation velocity with respect to the fluid ahead of it, then this is really a simple front tracking equation, as you know, and you can. And the point is that if at some time G is equal to 0 everywhere on the front, then and if G obeys this equation, then at all future times G will also be equal to 0 on the front, and so it's simply a function that lets you track the front. This is what the G equation is. So people ask, well, is it conservation of mass? Is it conservation of momentum? Is it conservation of energy? No, it's not conservation of anything. It's just a front tracking equation is all it is. The function g is continuous. It better be, and it better be differentiable. Otherwise, this symbol gradient g doesn't have any meaning. But typically, it's not twice differentiable, only once differentiable, because when these fronts propagate, well, they can propagate, for example, into each other. If it's a front, and form a cusp, and then there's a singularity at the cusp, so the second derivative no longer exists at the cusp. At a later time, the cusp would remain. So there's some mathematical, or if you like, computational, or whatever, difficulties in maybe in using such an equation, which which develops the singularities. The essential nature of the equation is that it develops the singularities, but it can serve to track the front.
So it does not depend on, I mean, it does depend on the curvature through the right-hand side term, but does it distinguish between concave and convex?
Yes.
Yes.
Yeah. In general, the flame speed will depend on the curvature, and it'll be different for concave and convex. For example, if this is the curvature of the front, and if the curvature is not too large, this linear dependence on curvature would apply. Curvature becomes larger; it's no longer linearly dependent on curvature. But if we're talking about the G equation, it's less than zero in reactants, it's greater than zero in products. What's done is, coupled with, if you're going to use it, you would couple it with, now the density is approximately constant in the fresh mixture, and it's approximately constant in the burnt mixture. So you can, at least for low enough Mach numbers, use a constant density Navier-Stokes equations in the reactant mixture, constant density Navier-Stokes equation in the product mixture, and then add that to the G equation, and so that then gives you a nice simple formulation, I guess. Different densities in reactants and products. It's a moving boundary problem because you don't know, but the G equation then would tell you how the boundary moves. And as you was just pointed out, the propagation velocity may depend on the curvature. It may also depend on the gradient of the fluid velocity, on the strain rate in the flow, and well, on the curvature, the geometry of the moving boundary. The fact that the point is that G is entirely arbitrary. All it has to do is be less than zero in reactants and greater than zero in products, and so there's an infinite number of functions that would satisfy that condition, and all of those functions would mathematically propagate the surface at the correct. What did I do? At the correct. No. At the correct velocity. Yeah. Right. That's the one I haven't talked about. And so if you're going to do what I was talking about, like computationally use Navier-Stokes here, and the G equation, periodically in the computation, the G can become very skewed, and so it's helpful to reinitialize, redefine G from time to time to get a smoother description of that function away, of that arbitrary function away from the reaction sheet, so that the computations then will receive more easily. And so reinitialization is what that's called, computational, and that's a standard thing to do when somebody's doing computations for the G equation, and periodically reinitialize. And so people ask me, what are the dimensions of G? What are the dimensions of G?
Dimensionless. Can be dimensionless. Huh?
It doesn't matter. It's linear.
It doesn't matter. You
It's a linear equation.
may
It's
choose
linear.
any dimension you like for G.
Make a distance function.
Yes. That's what Norbert Peters says. He says, I like to call it the distance function. So I'm going to let G be, say in a one-dimensional case, x minus the x value of the flame. That now you've arbitrarily given G a dimension. It's a length. And I prefer to be dimensionless. If somebody asked me what dimension I would want for it, I said, but Norbert says, no, if we make it dimensional, and we talk in the turbulent flow, you find a difference, a fluctuation in G, and this is a fluctuation in the velocity, V minus the average velocity, then you can average the G equation, and just as you do turbulence averaging for Navier-Stokes, he did turbulence averaging for G, for this particular G. And when he did it, then the root mean square fluctuation of G. So here's a turbulent approximation. If you average V dot grad G, you get the fluctuate, the analog of the Reynolds transport is V prime dot grad G prime bar, and the suggestion is to model that, model this thing. What is it? Well, I guess it's a length, huh? That's being transported by the turbulent diffusivity times the curvature times the magnitude of the gradient. With that,
It's almost impossible.
what's almost impossible?
What you wrote there, because on the right side you have something which can be positive and negative. On the left side you have something which is which is only positive, and it's nonsense.
Here?
Yeah.
This could be positive or negative.
Now go right.
This could be positive or negative.
No, it's only positive. It's absolute value.
No, the curvature is of both sides. The curvature is outside the absolute value. Curvature is both sides, positive and negative. Okay. And so this is. Yeah. Curvature is positive or negative. Curvature is not defined as, if it's burnt this way, it's positive. It's the other way, it's negative. Okay.
It's impossible to.
I mean, there are both positive and negative curvatures along this line.
I'm saying that there you have a square root of absolute value absolute value of vector is a square root of something. There you have just grad. It's absolutely impossible to get.
I have no square root. I have no square root.
If you change G to minus G, it would have different effect on the two sides?
Of course. In one you change, you have to change, in order to be consistent, you have to change curvature, which is impossible.
So this is Norbert's suggestion for.
So it's incorrect.
No,
On
but
the
you change
contrary,
sign to
it's correct.
The way the curvature is written, if you go to view minus the sign of curvature.
So the basis of this equation is it phenomenologically derived or motivated, or is it actually a derived equation?
No, it's phenomenology motivated.
Yeah.
It's not derived. This is an hypothesis.
Yes.
Just like Reynolds.
Yeah.
And do you have flux of G? Just correlation between fluctuations velocity and fluctuations of G can produce usual turbulent diffusion flux?
Yes.
You don't have this?
Besides this is simply the equation for the average of G.
Yeah,
And
I
it has
understand.
in it a turbulent burning velocity,
Yeah.
which is, Swami put this up yesterday.
Why you don't have here a term with Laplacian of G? Mean G.
There is an additionally, well,
Plus here?
this term has the character of Laplacian, but it's not exactly a Laplacian. But in addition, besides the equation for G bar, there's the equation for G prime squared bar for the average, and there are turbulence modeling in that equation as well, and you need an equation for, if you're doing the modeling, you need an equation for the curvature as well. And so, and all of those equations are in Norbert's book, but in a 50-minute lecture, we've covered, 45 minutes of it, and we're on slide number 3 of
Can I ask
30 of them.
Can I ask one question?
Yeah.
First, it's not clear how you can average equation, which is not field equation. Okay?
Yeah.
This is a few.
Why not?
Would you explain that? Where's the problem? This is a mathematical.
Because no, it's not mathematics. Because, for example, you take Navier-Stokes equation or other equation. This is a field equation. It's valid everywhere. Okay? G equation is valid just
No.
on the
Is that right?
no, just on this surface of the
Yeah?
plate.
No.
But I mean, you wrote down G is a function of x, y, z, and t.
It's a continuous equation.
But it's valid just on the surface.
No.
If I now take some transformation of G, another function, non-linear function, you will obtain another mean is a scalar surface. You can do that.
Yes, that's
So
And
what equation?
you can average. You have a function of space and time.
So
You can average it, right?
so it depends on the room and
What?
on the research who do that. For example, I don't like this distance. Okay.
You don't like it.
I
Then
like
you do something
other
else, and
function.
you're making a different theory because
Yes.
you have a different G.
But I will obtain other surface, mean surface.
You still will have the correct surface, but once
they are-
having done the modeling,
this-
of course, you'll get
The
different
surfaces
results.
will be different.
Yes.
Mean surfaces will be
Yes.
different. And for the
And so
surfaces,
Norbert
correct,
suggests that this is the useful selection for a specific.
it's useful, but it's useful, but not more.
Well, but it's not wrong. I mean, I mean, it's not self-contradictory. I mean, Zimont, I think, is the guy who keeps saying that you cannot do this. You cannot average. And Zimont, you're wrong. You can. Anyway.
It's not my problem.
Can you maybe clarify? Is that first of all correct that this equation is only valid on the front? It looks like you
No,
said it's valid
The
everywhere.
equation is valid everywhere. The equation is valid everywhere. It has physical meaning only on the front. Okay, and it's, if you look at Norbert's book, he does that in a very logical way. I mean, he points out that, and so he introduces things that have physical meaning, and this is kind of an introduction or a suggestion it's an introduction to the way that he does it and gets these
And another question,
Yes.
Forman. In
Yes.
fact, you spoke about propagation velocity.
Yes.
Do you remember Vijay equation?
Yes.
But why you speak about propagation velocity? Because, in fact, we want to describe the consumption of a mixture. So, we
Yeah.
have to modelize the product of a velocity. I don't know what velocity. Velocity multiplied by the surface.
Yes.
But it's not propagation velocity. Because there are some difference between propagation velocity and consumption velocity. So we have to
in
modelize.
general, yes.
So we have to modelize not propagation velocity,
Well-
but consumption velocity.
Well, locally, it's propagation. Locally, this quantity S is the propagation velocity for a flamelet. So the flamelet are propagating at velocity S. Now,
No, follow me, Kate. Follow me.
for the turbulent case, ST is well, when you ST is a turbulent, if you like, turbulent propagation velocity for and would in you know, there's if you had a statistically stationary one-dimensional propagation, then the propagation velocity would be the same as the consumption
For
velocity.
non-stationary case, is not the case. For non-stationary case.
We have a discussion, of course, after this.
Maybe, yeah.
And of course, that's exactly a very hot topic. We should probably use
Oh,
all
that's
this.
what I was supposed to do. I'm sorry, you told me I was supposed to put this stuff off for the discussion section. So let's address that more during discussion. Okay. I guess I've already said that. G equation can include pockets. I've said that. Diffusive is if these flamelets are unstable. If there's a diffusive thermal instability of the front, can I still use the G equation? Yes, I can still use it. Why not? Because it simply means that my propagation velocity of the front has to reflect the effect of that instability. The Lewis number is a thermal diffusivity, the fuel diffusivity. There are pulsating instabilities at large Lewis numbers and cellular instabilities at small Lewis numbers, and the idea of defining a G that breaks down only if the front breaks. Okay, this is Julien and Cleland's classical stability diagram for premixed laminar flame, flamelet, if you like. Beta is Zeldovich number, E over RT, Q over CPT, Lewis number -1, and so Lewis number equal 1 here. This coordinate is heat loss. If you had distributed heat loss, then this would increase, and at this point here, the laminar flame would be extinguished by heat loss. And there's a region in which the stability analysis shows, based on one step high activation energy, it shows that to all wave numbers, the growth rate is stable, no instabilities. There's non-planar instabilities with a growth rate that peaks at some particular wave number for small Lewis numbers, and there's regions of pulse of traveling waves, and finally a high Lewis number, beta LE -1 greater than 16, in which the stability is like this, and so the highest growth rate here, this is complex, and this is real, is a pulsation, and physically you can understand high Lewis number means high thermal conductivity, and high thermal conductivity and low diffusion coefficient. So you can imagine the mixture now, it has a high thermal conductivity as the flame here, right? Has a low diffusion coefficient, so the fuel isn't diffusing in. And so what's happening is that the fresh mixture is being heated and heated. It's getting hotter and hotter. But then there's all the fuel is there. And so eventually it gets hot enough so that all of that stuff burns roughly at once. And you get pulsations. And at high enough Lewis numbers, those pulsations become chaotic, and so there is chaos that's inherent in these front propagation at Lewis number greater than 10 or 100. It's certainly type 1, and you said it was between 10 to the 3 and 10 to the 7. So I'm giving the lower limit. This has got to be chaotic. I mean, there has to be chaos associated with the pulsating instability. It has to exist, even though people don't seem to find it in computation in supernova. It's got to be there. So I anticipate strong pulsating instabilities
It seems that in supernova it is quite different situation, in fact, because of matter is strongly degenerated, and there is no conventional turbulence. At the same time, relator instability is much more important because due to relator instability, flame sheet is broken and the separate bubbles which are going to the surface much faster than they are growing in the radius. So it is quite different situation.
What kind of? I didn't understand.
Relative.
He's talking about.
Relative
But these are
instability.
totally different time scales, the pulsating and the Rayleigh-Taylor.
And,
Oh, Rayleigh-Taylor, I'm sorry.
Conventional turbulence certainly doesn't play any role, doesn't important for supernova.
Oh, I see. Well,
I don't
Because
think that- I
we
don't
are
think
talking
that's
about
true.
very high density, yes, strongly degenerate matter
Yeah.
in supernova. So
Yeah.
you apply the same as Navier-Stokes and real gas. It's
just
certainly
wrong. Just plain wrong. You may well be right. That's just plain wrong. But computationally, people use ordinary turbulence. Nobody's done what you want them to do.
No, they've computed the Rayleigh-Taylor effects in supernova. That's the main way it goes unstable. You've seen those.
Situation is the following in supernova.
No, this is not.
We have a lecture.
But there's one point I wanted to make.
But
The
Rayleigh-Taylor
time
is
scale-
also. Yeah.
The time scales
That's-
would be so
Rayleigh-Taylor, you're
different
not
for the pulsating than for the Rayleigh-Taylor. The pulsating would be something like this, and the Rayleigh-Taylor would be much larger. And it's not clear to me what the pulsating would do, because no one's been able to evaluate it yet.
And if it's below the Gibson scale, then it's
Yeah.
not really felt at the larger scales.
Right, so we don't know yet.
Could be like a tempest in a teapot.
Yeah,
Mm-hmm.
it could be like a jitter, but nothing more than background noise.
Background noise. Oh well. Gee, and I was hoping somebody would explore the character of that chaos. Maybe.
Well, there are other
There's
good
no
reasons
point.
for studying it.
Well, I mean, I just want to comment that Frank Innes, I mean, he redid very detailed chemistry calculations for the thermonuclear flame, and we spent some time trying to figure out. He just doesn't see it for some reason, even though the explanation is very intuitive. It has to be there, and it's not clear why we're not seeing it. Whether it's either it's a very small effect or and numeric just doesn't pick it out.
There's a lot of things that Americans can't pick up.
Yeah, so it's possible, but it's not clear why.
Yeah. Well,
When is it next?
I don't know. Yes. Okay. The effective Zeldovich number. Right. Yeah. Are you ready for the second hour of the lecture? I think it probably. you're very rapidly going to see all the rest of this lecture, okay? Lean hydrogen flames actually do break up into cells with spaces between them, so that you really couldn't use the G equation to describe those because it's broken, okay? And computationally, Joe Gertcher showed, as well as experimentally in the previous, that happens for lean hydrogen. And the other day, somebody showed me 18 steps, and I thought it was larger, 21 steps. This is the San Diego mechanism for hydrogen. Only 21 elementary steps, which there's lots to be said about that.
Very different.
But trouble is, when you get to lean hydrogen and measure the burning velocity, computationally you can calculate it pretty well. Only 7, except at high pressures, only well, 7 steps, 3 reversible 10 steps will describe. There's a significant difference, and Sorey is important here, not unimportant in the planar case here, but the computation is well below the measurements. There's a 1-step approximation that's good and for these lean hydrogen flames, based on the detailed chemistry. There's uncertainties in the deflagration velocity. This is showing in more detail how the computation for the planar flame differs from the experiment. Jerry Faith, others have done the experiments, shows in more detail how that difference can be more than a factor of 10 as you approach the lean flammability limit. The reason is flame ball, and so a flame ball can be used as a model in an extremely lean case, and I'm suggesting instead of a propagating front, a propagating group of flame balls, and you can do mass conservation for that. The flame ball radius, classical activation energy asymptotic results for flame ball radius, burning rate of the flame ball, comparison with classical. If you make these fit, if you think in terms of flame balls, the data are like this, and force it fit here, and use the classical planar result, you get something that can't agree as well as the flame ball array can. So array is important for the flame ball structure. It's included here. The lean flammability limit is a limit in which the flame ball can no longer exist. If the flame were planar, the limiting equivalence ratio would be 0.27. For flame balls, it's less than 0.074. And Sorey becomes important in the limit, so important that actually, crossover temperature, actually so important that actually you think that for equivalence ratios less than 1, hydrogen should be the limiting reactant. Actually, it's a limiting reaction only for equivalence ratios less than 0.24 because hydrogen is attracted to the flame, and so it becomes the limiting reactant. So oxygen becomes a limiting reactant for actually lean flames, lean hydrogen flames, because of that. It's calculated at the maximum temperature as a function of the equivalence ratio, and this would be the lean limit for flame balls, and comparison of the calculation with space shuttle experiments of Romulan flame ball radius versus they start off larger, and when they become study flame balls, then they're approaching this limit. In Eduardo...
Sorry, what is phi?
What?
Phi? What is phi?
equivalence ratio.
Ah, right, sorry. Mhm.
Yeah. So, and so the theoretical limit for hydrogen is 0.7 down there. Yeah, see, I told you. Oh, yeah, so that was 5 minutes, that wasn't bad. So these are the conclusions. I guess I don't have to read them, I'll just leave them there. So I thank you then all for your attention.
Jim, you're the chairman.
Oh, you're the chairman, okay.
Is there any question?
Questions, or should we?
Yes. Ask for the question, yeah.
Orman, your first conclusion, you mean very lean hydrogen deprivations where there's local extinction or breakup of the surface? Is that
Well, it doesn't have to be all that lean, because you start to get this phenomenon already at this condition here. Is equivalence ratio of 0.5. This happens to be downward propagation in a 2-inch diameter class standard flammability tube. Toru Matani did these experiments, and I don't know if you can see, there's this finger, this finger, this finger. So an equivalence ratio of 0.5 under these conditions, you can't see hydrogen flames, and so we added a 0.25% with CF3BR, made them more visible. It didn't really affect the propagation, but it made it possible to photograph them. And so you can't use a G equation for that. I'm pretty sure. Yes.
Do they see flame balls too with increased diluent, or is it just a stoichiometry?
Yeah, they had increased diluent. So this is somewhat diluted. It's not exactly air, right?
I mean, as you decrease the diluent, you can see the flame balls forming.
Yes, as you have, yeah, you tend to see it more in diluted mixtures. Yeah, if you add.
But it doesn't, if you keep the stoichiometry constant,
Yeah.
and decrease.
There is an influence of the dilution that fixed stoichiometry.
When you are talking about flame velocity, especially in case of strong turbulence, when flame sheet is broken, then it should be more clear defined what is the meaning of the flame velocity. Velocity of the flame propagation or burning rate, because if you have, like here, you have shown broken flame sheet, then there are bubbles which separated from the main flame sheet, and what is the meaning of the flame propagation, velocity of the flame propagation? And similar situations with supernova as well.
Yeah.
Here, for example, what is the meaning of the flame propagation?
Let me see. There are two ways. I don't know what you mean by broken flame sheet. If by broken flame sheet you mean this picture here, these are not broken. It's simply that islands have been formed by flame propagation. These are not broken. If you break the flame sheet, you don't have a G equation. Period. You know, anything broken, you don't have it. These are not broken, and so this complex in a homogeneous situation would be propagating steadily at a turbulent burning velocity, which would be the same in this statistically stationary situation as the consumption velocity. What are we terminology we use? Consumption velocity, the integral of the reaction rate over the whole thing. Right. And so, and these locally would be propagating at the laminar flamelet velocity at whatever the local laminar flamelet velocity is, because that velocity depends on the curvature and on the fluid dynamical strain rate of the flow in front of it. And so there is an interaction between the flame and the turbulent flow, because the density changes affect the turbulence. Increases the scales of the turbulence, for example, significantly in going from fresh to burnt mixture. But all this stuff could be described by a G equation. You don't.
But I would prefer to think about two different things, two distinct.
Yeah.
One it is local velocity of the reaction propagation, and another one it is burning rate.
Yeah.
Then we can make difference.
Yes, in general, these will be different. I mean, the displacement velocity, whatever, will be different from the.
Sure.
Yeah. And only in a special case would they correspond. But I'm not sure. I mean, why is Rayleigh-Taylor turbulence different from Navier-Stokes turbulence? Once it gets turbulent, you say it's different or something?
It comes from the Navier-Stokes equations.
I think so.
Yeah, it's
I mean,
just-
are you telling me that there is no Kolmogorov range?
The buoyancy cascade obeys different scalings. The buoyancy is a dynamical quantity, and the cascades just dimensionally end up with the so-called Bolgiano spectrum. Eventually it transitions over to the Kolmogorov spectrum. Whether that detail matters as much in supernova is another question.
I see.
It's a little bit now.
Bernard, that wall?
The gravity is so high and varying.
Yeah.
It's not really, it's Rayleigh convection, let's just say, broadly speaking.
So the accusation is that with Taylor instability we are in the Bolzano scaling regime. Is that confirmed actually from theory and simulations? Because
No, it's controversial. I mean, it's a logical theoretical interpretation. Well, Chertkov has an interesting discussion as to the fact is there's an ambiguity. In principle, there's nothing that compels Bolgiano versus Kolmogorov. They're both internally consistent, so we might call it a pattern selection problem. And Chertkov has an interesting argument as to why Kolmogorov should dominate unless circumstances such as the boundary layers and Rayleigh-Bernard interfere. Or maybe it's the other way around, that the boundary, somehow some of the boundary layers and Rayleigh-Bernard allow Bolgiano.
It's a time-dependent flow. Intrinsically time-dependent flow, and Bolgiano has been derived and has been shown for steady flow. And here you have expanding situation, and trivial stuff doesn't work.
And Bolgiano originally, of course, thought of a stably stratified atmosphere.
Absolutely. No, okay, but this has been proven.
Right. Anyway,
but still, it has to be
we of course have the opportunity to go for more detailed discussions right afterwards when we go back to the Nolita building. But are there any other questions before that?
I have a small question for me.
Yes.
Could you return to the diagram, Dan Köhler-Reynolds?
Yeah, you want to go back to the diagram, okay. That one.
In fact, I'm not sure that I understood your idea when weak turbulence. In fact, when we can imagine a situation that the chemical time is very short, and that we fix turbulence levels number. So we can have very strong turbulence because U prime can be much larger than laminar velocity, so it's not weak turbulence. It can be strong turbulence.
Well,
I am not sure that.
No, this is the turbulence Reynolds number here, right?
But you fix.
So
You fix.
you move out here, you're getting stronger.
No, you fix turbulence Reynolds number. Okay. You fix even very large.
Okay.
and after the chemical time can be very short.
The chemical time, right? And that gives you
Yes, you go up.
Yes, yes.
So the turbulence can be extremely high intensity in comparison with the laminar velocity. Why you write weak turbulence?
Why are we
Yeah.
turbulence? I mean, I write weak turbulence
In
because
what sense?
the
No, it for each Reynolds number.
U prime is much less than SL.
In the sense of the Reynolds.
For example, for supernova, I don't know exactly what is the chemical time, but maybe the chemical time is very short, so we can have a huge Reynolds number, but the turbulence can be
chemical time, you mean a huge Damköhler number?
yes, the Damköhler number is very large,
Yes.
but turbulence can be also high intensity.
Turbulence can be high intensity, that's
So it's not weak turbulence.
You don't say that.
I mean, it's there.
No. I fix the Reynolds number. I fix the Reynolds number, and I go up.
Maybe the question at this point is, what is the factual evidence for saying that the line is really inclined at this angle?
It's a relative concept.
Do we have factual evidence for the fact that the line has a
No, divided by itself.
There's no claim that the line has a slope.
It's not relative.
On the left side,
But this quantity here is a measure of the turbulence. This is a fixed turbulence intensity of the line compared
It's everywhere.
to a burning velocity. So this is a fixed ratio, and so this turbulence intensity here is 10 to the minus 4 times the laminar burning velocity. And so the laminar burning velocity is much higher than the turbulence intensity above this line. And so above that line, where the 10 to the minus 4, that means this laminar flame is going so fast, except it's a square. So 1% of it is influenced by turbulence.
SL is also you
The
can
thing is that there's a small deviation from planarity on an area.
because the time scale.
Yes.
All right, so that's your option. You haven't given until now an operational definition of weak turbulence.
Well, I just, okay, sorry.
Right, that's at this point.
Yes.
And so we just have to ask what parameters give that condition.
Yes, yes,
And U prime much less than SL is an obvious,
yes, yes.
criterion.
Yes, yeah, that's the
So it's correct? Is it correct?
Whether that follows, I don't see the problem is that that Damköhler number, I don't know how it relates to U prime or SL. I mean, I know the answer in terms of U prime or SL. I don't know the answer in terms of the vertical
Well,
coefficient.
this slanted line is constant value of turbulent kinetic energy to square of laminar burning velocity.
Yeah.
And so,
So that's
this value here it's 1, here it's 10 to the minus 4.
Foreman.
And so my suggestion is not there, but it's above this line.
So you don't have to reason about Damköhler number in terms of the weak turbulence criteria. If you were down a hypothetical flame sheet, you have an objective meaning to U prime over SL independent of any chemical timescale. You call the timescale nominally 0 for chemistry. You still have U prime or SL can be small or can be large. So the Damköhler is not a good coordinate for this particular discussion.
Right. That's why this line is like this. And that's why the coordinate is this one.
Yeah.
The Borghi diagram.
Yeah.
But if my idea, if we fix laminar coefficient diffusion, which governs by laminar velocity flame, and we go to zero laminar, we go to the zero laminar molecular diffusion coefficient and chemistry time in such manner that SL laminar velocity is fixed. Okay, so we can have the situation very extremely high turbulence with a very big Damköhler number.
Yeah, that's down here. Yeah, that's out here.
Oh no,
That's here.
no. We can at each Reynolds number we can find the high intensity turbulence.
No, look. I mean, KL is U prime squared. Okay. you want to keep the lavender burning velocity fixed, right?
Yeah, I think
KL is perhaps
there
where
will be
the
more
rest
opinions
elsewhere.
on this. Victor just claims you have to have additional input to that.
No,
But we should, of course,
4 minutes is absolutely right. What is strong or not?
no, wait, now it doesn't make sense.
If chemical time is much shorter than electron time, period. This is interesting. It's a big turbulence from this point of view.
Yeah, Vladimir didn't listen though, so then we need to go again.
We
have a discussion.
Free beer in the Nordea building.
Yeah, exactly. So before we go over, one more thing.
Any beer you find here is for free.
One more thing. There's, after the discussion which Jim will lead, there will be a barbecue outside Nordea at 5 o'clock, which is spontaneously organized by some of our guys at Nordea. So it's completely informal, but please help and enjoy it. And so let's thank Coleman again.
Barbecue, spontaneous combustion.